Hello and welcome to Self-Driving Cars, lecture number 4 on reinforcement learning. In lecture number 2 and lecture number 3, we have seen how end-to-end self-driving models can be learned using imitation, by imitating an expert's behavior or by trying to predict expert affordances. In this lecture, we're gonna talk about another technique, a very popular technique in robotics called reinforcement learning, which allows for learning robot policies without such expert demonstrations. This lecture is structured into 4 units. In the first unit, we're gonna define the reinforcement learning problem formally through the framework of Markov decision processes. In the second unit, we're going to have a look at the Bellman equation and how this leads to one of the most fundamental algorithms for reinforcement learning, which is called Q-learning. And then finally, in unit number 3, we are going to have a look at a deep neural network-based version of Q-learning that's called deep Q-learning, as well as its variants. Let's get started with Markov decision processes. So far, we've considered supervised learning. Imitation learning was a supervised learning problem. It required lots of expert demonstrations, and we're basically trying to mimic an expert. Now, the disadvantage of this is, of course, that first of all, we have to have access to these expert demonstrations, but also these loss functions are actually not the loss functions that we want to optimize ideally. They are auxiliary loss functions. They just tell us we want to be close to the expert, and they have a very short-term effect. For example, in imitation learning, we have a per frame loss on the action. We don't look into the future. We don't anticipate what happens in the future. Only implicitly we do that by trying to mimicking the expert. And also in direct perception, we've seen that we put per frame loss functions on the affordance indicators. Now, what we're going to consider in this lecture is different. Here, we're not going to try to mimic an expert. Instead, we're going to try to learn models based on the loss that we actually care about through exploration and exploitation and interaction with the environment. And these loss functions are very different from the standard loss functions like the L1 loss on the steering angle that we've considered for imitation learning. These loss functions are much more general. It's a much more general framework. For example, a loss function could include that we want to minimize the time to the target location, which is something that we want to do in self-driving, or the number of collisions, or the risk that we take while driving, or that we want to maximize the comfort, etc. So very general definitions of what we want to achieve, and we can formalize self-driving in terms of such general loss functions in the framework of reinforcement learning. In machine learning textbooks, reinforcement learning or learning is typically categorized into 3 different categories. The first category we've seen already. This is the classical machine learning framework. It's called supervised learning, where we have a data set of XY data label pairs, and the goal is to learn a mapping from X to Y. Examples of this include image classification, regression, imitation learning, affordance learning, and so on. In contrast, in unsupervised learning, we're only provided with a data set, and the goal is to discover structure underlying the data. Examples include clustering, dimensionality reduction, feature learning, and so forth. And this type of approach has also been used in the context of self-driving. For example, when learning world models of the environment using a simple reconstruction loss, an image reconstruction loss, in order to learn a good compression of the high-dimensional state. And then finally we have reinforcement learning, which is what we're gonna talk about in this lecture, where in contrast to the first two learning types, an agent interacts with its environment. And the environment provides numeric reward signals to the agent. And the goal is to learn, the agent should learn how to take actions in order to maximize the reward that's provided by the environment. And examples of this are to learn manipulation tasks, with robot arms learning to grasp objects, for example, or control tasks, as we're going to see today. Reinforcement learning can be formulated or illustrated with a simple diagram. We have an agent that operates in an environment. The agent could be a self-driving car that operates in a real-world environment or in a simulated environment like Kala. The agent observes the environment state st at time t. This is indicated here by this arrow. The environment provides or exposes its state, or exposes partially its state to the agent. Typically you don't have the full image of the environment, you don't have the full state, but you just see parts of the environment. For example, a car might just take pictures, so you don't get the 3D state of the environment, you just have a 2D projection, maybe just of a certain area of the environment, not the full world that the agent operates in. It's just a projection of a very small part of the environment. So the state is not complete, typically. And then the agent sends its action AT at time t to the environment. Based on the current state, it tries to make the optimal action for that state, for that observation. The car observes an image and tries to turn the steering wheel appropriately according to what it sees. And then the environment returns two things to the agent. It returns the reward, it computes a reward, it tells the agent how good that action was. For example, if the self-driving car has reached its goal, it tells the car this was good. Or if the car has run over a pedestrian, it tells the car this was not good. Or if it ran into a traffic light, it tells the car this wasn't good. You produced a crash, it wasn't good. So the environment returns the reward, it judges the action AT, and that's what we call RT. It's a numerical number. It's just a simple number and can be either positive or negative. And the agent wants to maximize the reward, wants to have as much reward as possible and minimize the negative reward. The second thing that the environment returns is the next state. The environment, given the action from the agent, and of course also the action of all the other agents in the scene that are, for example, simulated in a simulator like Kala, the environment transitions to the next state. For example, if the agent moves forward, the environment provides the image at the next camera location back to the agent. That's the observation st+1. So the goal in reinforcement learning is to select actions to maximize the total future reward. The environment provides a reward, and we want to have as much positive reward as possible. However, the actions may have very long-term consequences. For example, in self-driving, we might have a reward only when reaching the goal. This might happen after 1 minute of driving, after 30 minutes of driving, after 2 hours of driving. And we might not have a lot of reward until we get there. This makes the learning problem really hard. Reinforcement learning is a really hard problem. Also, the reward might be delayed and not instantaneous. The environment may not immediately give you the reward despite you made a good action. It may be better to sacrifice immediate reward to gain more long-term reward for the agent, therefore. And there's some examples, and this illustrates how difficult that problem is. The agent needs to decide in the short term. It needs to decide for the next action, and it may need to decide for a suboptimal action in order to get a really high reward in the long run. And an example include, for instance, financial investments, which may take months to mature. Or consider, for example, a rescue helicopter that needs to rescue a person, but that is running low on fuel and needs to be refueled. So refueling takes time, but it might prevent a crash in a few hours ahead. Or maybe a very prototypical example is a chess game where sacrificing a particular chess piece, which in the short term leaves you with less pieces on the board, but in the long term might help you win the game. So this makes the problem really hard. Now let's look at some concrete examples to get a better idea of how different reinforcement learning problems might look like. And one of the simplest is the so-called moving cart pole balancing problem, where we have a cart here that can move left or right, and we can provide a force to that cart in order to move it to the left or to the right. And the goal of this, the objective here, is to balance the pole on that moving cart. So we want to have that pole upright. And it might be that in the beginning the pole is actually facing down, so we have to lift it up. The state is the angle of that pole. There's a joint here, so this is the angle here. And also the angular velocity, so the first derivative of the angle. And then the position of the cart in x direction, and also the velocity of the cart. So we have a four-dimensional state space, a very simple state space compared to self-driving or other things. And also in this case, it's actually fully observed. Right? It's not like in self-driving, what I mentioned before, where we have just a picture that doesn't see everything, but here we see everything. We have just these four values. Now the action is to apply this horizontal force to the cart such that the pole is upright, but the reward, as you can see here already, is very sparse. The reward is 1 if the pole is upright at time t, and it's 0 otherwise. So if the pole is facing down, the system has to experiment, the agent has to experiment with the environment in order to actually observe the first reward, which makes the problem very hard. And this problem can be made even harder. Like this pole balancing problem can be solved by humans. It's hard. You can try it yourself, putting a pole in your hand, trying to balance it. It's hard, depends on the pole, but you can do it. But adding more joints and adding more pole segments makes it even harder. But robots can solve this control task, and I have a pretty neat demonstration of such a inverted triple pendulum here. You can see how this robot is able to swing their pole up despite this complicated setup. Impressive, no? I find this really impressive. Another example is robot locomotion. This is a example taken from the RoboSchool environment from the OpenAI gym, where also our self-driving takes place. This is just another environment in OpenAI gym. The objective here is we're given a robot that comprises several bones and joints, like the articulated structure of the robot. And you can see there's different robots here. And the objective is to make the robot move forward. And the state is the position and the angle of all of the joints. And the action is the torques that we can apply on the joints. Similar to the cart pole balancing problem from before, but now a much more complicated articulated robot. And we want to learn how to move. The robot doesn't know anything about how to move, so we want to learn how to move. And the reward is 1 if the robot is the agent is upright and moving forward. And it's 0 otherwise. And so here are some examples of what these robots have learned using reinforcement learning. So they have actually learned, they have come up with a strategy for being upright, not falling down, and at the same time moving forward as quickly as possible. You can see interesting behaviors emerging, and some of these behaviors are actually similar to behaviors that also real creatures have learned. Another example, Atari Games. Here's the Gym retro environment, also from OpenAI Gym. And it provides a whole bunch of Atari games, which you can see here, that directly come with a reward because they have a game state, they have a score. You can see your score inside that game. You can retrieve your score from there. And that's something you can use as a reward to try to learn each of these games. The objective is therefore to maximize the game score as the reward. And the state is simply the raw pixels of the screen, 210 times 160 pixels. And for some of these games, it's really easy to learn using reinforcement learning. And the games that have really complicated behavior and require very long-term planning are much harder to learn. The actions are the standard actions you have on a keyboard, left, right, up, down. And the reward is if the score increases or decreases at time t. And that's what you want to maximize, the game score. And probably you have all heard of AlphaGo and the successors. And this is also a prominent example of reinforcement learning, in this case combined with classical planning tree search techniques.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
They said all is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness?
Ooh.
Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Well, look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, it's made a mistake.
He's got to pronounce America.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
There's even a movie now about AlphaGo. The objective is simple, winning the game. It's fully observed. The state space is simple, but it's extremely large because of the many situations that can occur. And so the state is just the position of all the pieces, and the action is the location of the next piece. The definition of the environment is super easy. The reward is 1 if the game is won, and 0 otherwise. A very long-term reward, extremely long-term reward, which makes it hard. And another example, self-driving, of course. And you're going to see this in the second coding exercise, where we're going to try to develop an agent that drives well in the OpenAI car racing environment and tries to pass as many grade tiles as possible just by learning through reinforcement learning. And this is one of the agents here driving. Here in this case, the objective is lane following, and the state is also the image, 96 times 96 pixels. Actions are acceleration and steering, and the reward is minus or negative if we continue to the next frame. So with every frame we get a negative reward, and we get a positive reward for every gray tile that we pass. So we want to pass, in other words, we want to pass as many gray tiles as possible in as little time as possible. So here's again the reinforcement learning loop that we've seen before. How can we mathematically formalize the RL problem? We do this using the so-called Markov decision process. The Markov decision process, short MDP, defines a tuple, S, A, R, P, and gamma. What are these 5 components of this tuple? S is the set of all possible states. For example, in the game of Go, the set of all possible, the combination of all possible pieces on the game. A is the set of possible actions. And R is the distribution of the current reward given the state action pair. So given a state action pair, the environment, as we already mentioned, returns a reward. And because that could be stochastic, we're going to consider the most general case here. We are having a distribution. It could be deterministic, given a state and action. It could just be a function that maps to R, but it could also be a distribution. There could be uncertainty in it, which is often the case, for example, when we have games or uncertain observations due to noise in the measurements, where things are uncertain. So the distribution, we consider distribution of the reward given a state action pair. Then P, the 4th element of this tuple, is the distribution, again stochastic, because it could be stochastic. The distribution over the next state given the state action pair. So it's P of ST plus 1 given ST and AT. This is how the environment transitions to the next state. And gamma is the so-called discount factor, which determines the value of future rewards. It downweights the value of future rewards because the agent can only look ahead so many steps. And so we can't typically, it doesn't make sense to consider the reward at like 1 million years into the future as high as the reward, say, 1 minute into the future. And this is what this discount factor is responsible for. And we're going to talk about this in much more detail in the next unit. Almost all reinforcement learning problems can be formalized as Markov decision processes. That's why they provide this powerful mathematical framework in which we are going to operate in. They are called Markov decision processes because they obey the Markov property. The Markov property says that the current state is completely characterized. No, the current state completely characterizes the state of the world. So what this means is that a state ST is Markov if and only if P of ST plus 1 given ST equals P of ST plus 1 given as 1 to ST. In other words, the current state depends only on the previous state. And if the previous state is given, all the states that come before the previous states don't matter anymore. This is the Markov property. And you may be familiar with this already through, for example, the hidden Markov models or the Kalman filter, etc. So here are some statements that are equivalent about this. For example, the future is independent of the past given the present, right? Or the state captures all relevant information from the history. Once the state is known, the history may be thrown away. And the state, ST, is the sufficient statistics of the future. We don't need to know the previous states. Now let's come back to the reinforcement learning loop, which we have already seen, which is shown here on the right. And let's now look at this loop in the context of the Markov decision process that we have introduced. We start at time t equals 0. At time t equals 0, the first time step. In the first time step, the environment samples the initial state from the state distribution P of S0. So we get the first state. Then for t equals 0 until we are done, until the end of our simulation, the agent selects an action, AT, or until the end of the rollout. It's sometimes also called a rollout. It's a rollout of the policy in the environment, interacting with the environment. So for t equals 0 until done, the agent selects an action, AT. And then the environment samples the reward, RT, given the state and the action, and also the next state. And the agent receives the reward and the next state and selects the next action, and so forth. How do we actually select an action now? Well, we know already the mechanism to selecting an action. It's called a policy. We have seen policies in the context of imitation learning, and we're going to look at policies here in the context of reinforcement learning again. A policy, pi, is a function from state space to action space that specifies what action to take in each state. Given any state, this function tells us what action we should take. And the policy is what we want to learn. It's typically a neural network parameterized with some parameters. Or it's a lookup table if it's a discrete state and action space. A policy therefore fully defines the behavior of an agent. And there are deterministic policies where we have a direct mapping. It's a function that maps from S to A. And there are stochastic policies that are modeling the uncertainty, that are giving us back a distribution. And we denote this as pi of A given S, which is a distribution P of A t equals A given ST equals S. As a little remark, MDP policies depend only on the current state, as you can see here, and not the entire history. However, the current state may of course include past observations. That's just a matter of how we define the state. We can define the state as a buffer of frames, for example, buffer of the last 10 frames of images that we have observed as an agent. And that's perfectly fine in this formalism. It's just a matter of how we define the state. Now, how can we learn a policy? We've seen already one way to do so. It's called imitation learning. We learn a policy directly using supervised learning from expert demonstrations. In reinforcement learning, however, we assume that there is no expert demonstrations given, and instead we learn a policy through trial and error. The agents discover itself which actions maximize the expected future reward. That's the quantity we want to maximize. In expectation, how much reward we get in the future. We want to take the action that maximizes this. The agent interacts with the environment and obtains a reward, and the agent discovers good actions and improves its policy, pi, based on the rewards that are given to the agent through this trial and error game. So how do we discover good actions? Well, we need to explore the state action space. And this is also what makes RL often unsafe and hard to execute in the real world. And there's the whole research branch on how to make RL safe. But of course, if we are in a simulator, if we're simulating self-driving in Kala, that's much easier because we are not posing any safety risk, and we can also simulate and explore unsafe scenarios. Because we need to explore the state action space. We know nothing. We don't have an expert that we could try to imitate. We combine two tasks here. These are the two fundamental tasks of reinforcement learning. The first task is called exploration. The goal of exploration is to try a novel action A in a state S, and then we observe the reward RT. We don't know if that action is a good one or a bad one, but we don't care. We just want to see what happens. That's why it's called exploration. Exploration discovers more information about the environment, but sacrifices the total reward given during that episode. Because we are trying an action, and in most cases, this action will actually not be a good action. However, through experiencing new states, we might potentially find an action at some point that's really good. And so we can learn from that and try to execute that action more frequently in the future. So exploration is particularly useful in the beginning when we know nothing about the environment. We need to explore. We don't have really any other choice. We need to explore in order to find useful actions. An example in gameplay is to play a novel experimental move. We don't know what's happening. We're trying it out and we'll see where this leads to. The other fundamental task in RL is called exploitation. In exploitation, we use a previously discovered good action, an action we know was a good action. And of course, by using an action which we know is good for a particular state, by exploiting this information, we are maximizing the reward because we know it's a good action. But at the same time, we sacrifice unexplored areas. If we only exploit, if we found a few actions that are good, but we haven't considered a huge part of the state space where maybe even higher rewards can be obtained, we are in a loop where we're just exploring that space that we have already, that we know already, and we get only this small reward in a sense, right? And so the game playing example here is to play the move you believe is best. Which means in practice, there's a trade-off between these two. You need to trade off exploration and exploitation. It's important to explore and exploit simultaneously. In the beginning, you want to start with exploration. And the better your agent becomes, you want to go more towards exploitation because you're operating in a better regime already. But how to balance exploration and exploitation? There's the so-called epsilon greedy algorithm that does exactly that. The epsilon greedy exploration algorithm tries all possible actions with non-zero probability. In particular, with probability epsilon, it chooses an action at random, complete random, and that's exploration. And then with probability 1 minus epsilon, we choose the best action. That's exploitation. And the greedy action is defined as the best action which was discovered so far, right? So the best action is the greedy action in a sense. You're looking at all possible actions for a state. You're looking at your current policy and you're maximizing that in order to exploit. With 1 minus epsilon probability, you're doing that exploitation move. And with epsilon probability, you do the exploration move. And as already mentioned, in the beginning, where you know nothing about your environment, you have to explore. And therefore, the epsilon schedule is such that in the beginning, you choose a large epsilon and then gradually anneal it. You gradually reduce it, make it smaller over time so that you go from exploration to exploitation. When your policy becomes better and better, you want to exploit more. You want to exploit the areas of the state space that are good, that give you high reward, because maybe you find some even better reward if you explore in those highly valuable regions and not explore randomly everywhere.